Yeah, I started the recording.
Okay. Cool. So yeah, so I think the last couple of weeks we have been looking at the trouble with distributed systems. And if you guys actually look at what Martin Klepman says about this chapter, he kind of mentions that this is the most depressing chapter that he has had to write because there's so much trouble going on with distributed systems, right? Like that's exactly the how he actually kind of puts it. And like he says, if you guys are looking for optimism, like this is not the place because it's going to be more and more pessimistic, right? Like the main reason, as we can actually understand, is like the networks are pretty unreliable, right? Like so, like a request goes from the client, you don't know whether the request reached the server, you don't know whether the server started processing it and failed, you don't know whether the server finished it and failed, and you don't know whether the server actually finished it, it didn't fail, but the request actually got lost, the response actually got lost in the network, right? So those are the three different places we can actually see in the diagram over here where the networks are really unreliable. We saw that. And so which simply means that even having a meaningful timeout becomes a challenge, right? Like, so do I have to wait like should I have to like wait for a shorter amount of time, or do I have to wait for a long amount of time? What are the trade-offs for each of those, right? So we kind of saw all those stuff. And we also saw about the fact normally we don't consider this, right? So I think that was one of the most surprising facts that only reading this book kind of gives an idea as to how important this unreliable clock issue is, right? Like, so like if your clocks are not synchronized, you cannot compare two different timestamps, right? Like, which means you cannot order events. You don't know, even if you use last write wins, right? Like, so a write that was actually done by a previous write can actually win if it actually has a higher clock skew, right? If its time is in advance, right? Like, so so everything becomes even more unreliable, like in the context of unreliable clocks. So are there solutions for this? There are. Like Spanner, for example, has a solution, like where they use very high precise atomic clocks, right? Like, so very costly ones, like that uses, I think it uses a kind of a rare metal. I forgot the exact name, palladium or palladium or something like that, right? So, like, because our normal clocks that we have in our machines, right? So those are just quartz crystal based ones, right? So their margin of errors are very high. But the atomic clocks that they mention over here, they actually use very high precision metal that can resonate with very high precision, which can actually lead to like very less amount of uncertainty about the time, right? Like, so so Spanner uses that, and in spite of that, even with that, right, like the time, like you have to ask someone, right? Like, so, and then there has to be synchronization, which means there is a little bit of network that is always involved, so there is always a little bit of loss of precision, right? Like, so kind of Spanner kind of handles it in a way where they have this like, okay, this is the maximum delay, right? Like, I think they mention it somewhere between 7 to 10 milliseconds. There's a maximum delay between any two nodes in the cluster, right? That's how Spanner kind of puts a max bound, and then they use this concept of true time, right? Like, I think probably we'll look at later Spanner in detail, where we can try to understand how true time really and beautifully works, right? But again, like with respect to what we saw last time, like everything is unreliable. And like you can't actually order the events based on timestamp because the timestamps are not comparable anymore, right? Like, so, and then finally, I think the last portion of like your networks are unreliable, there's a lot of queuing and stuff, your time is unreliable, and also the fact that even your processes, right? Like, so let's say a packet reaches ultimately the destination, right? Like after going through the entire network and all those things, uh, the system that is supposed to handle the packet could be really heavily loaded, right? Like, so because it needs to get a free thread that has to be run on a free core, right, in one of the cores of the CPU, right? Like, so that that particular packet can be processed, right? So there could be, so there is a queuing that can happen over there that can actually also result in a delay, right? Like, so this is the general theme that we actually saw until last week, right? Like, I think for the last couple of weeks, Abhishek has been dealing with this one. So like it's a pretty like it kind of portrays the grim scenario of where we are in distributed systems, because we are trying to build reliable networks out of unreliable components and stuff, right? Like I think that theme we also came across one more theme, like where what is what is the main goal of TCP, for example, right? Like so like TCP tries to provide a little bit of reliability on top of this unreliable networks, like by having like sequence numbers, by having acknowledgements. So it kind of gives you a reliable transformation, right? Like so you have to build at the top layers like some kind of reliability on top of it, right? Okay, so given that, so the goal of this chapter is, like I think we'll deal with consistency a little bit more, and then we'll also look at the issues of consensus. I think probably for today we'll stop with consistency, but by the end of this chapter we'll actually look at why consensus is hard, and how can we actually approach it. Right. So so one of the assumptions that we are going to make for this particular for the concepts in this chapter is we'll assume that all the problems that we discussed over the last couple of weeks still exist, right? Like so we are still operating over those unreliable networks with clock skews and with like unreliable like process passing times and stuff. Right. So so one thing that Kleppman actually starts talking about is like it's always useful to build. I think it's a general software paradigm, right? Like so it's always useful to kind of build a very abstractions, right? Like so and then you can actually associate certain guarantees with those abstractions, and then you can assume that those abstractions exist, those guarantees will be fulfilled, and not question those, right? Like so, and I think like the way he explains, even for example, all those transaction isolation levels, right? Like so like the way they have defined it is like, okay, fine, it can guarantee you like some kind of atomicity, and then some kind of isolation, right? And then some kind of durability, right? Like you can assume that those give for a specific transaction isolation level, like you can assume that that these are already in effect, right? And then you can try to build systems like with a basic set of assumptions, right? So so that's one theme that he kind of talks about, like it's always useful to assume like some useful abstractions, and it's always helpful to assume those useful abstractions and some guarantees about those abstractions, right? So and then I think so the first thing that we are going to talk about is consistency, right? Like so especially so the consistency that we are going to talk about here is actually the C in the CAP theorem, right? Like and then so this whole problem of, if you guys actually look at it, right? Like so if I have a single node, and let's say I have a single thread that's currently handling my right? Like so and assuming the write is atomic, do you guys actually think there would be any consistency related issue over here?
Well, if there's a single node and single thread, there would not, right?
Exactly, right? Like so when there's only one node, and then like when there's only one thread, like that's kind of handling your writes, there is always a single, and of course assuming that the writes are also atomic, right? Because if it is not atomic, so why is this atomic coming into picture, right? If it is not atomic, then what's going to happen is that particular write is going to be done as not as a single visible step, but into multiple steps, and some of the partial results in intermediately can actually become visible to the outside world, right? So that's why we kind of always mention that it's kind of an atomic, right? In which case, right? Like so, in which case, like as you mentioned, like we don't have to worry about like anything to do with consistency, right? Like you're always guaranteed to be like have a single source of truth, fully consistent. Let's say, so what does it mean, right? Let's say if someone says a write succeeds, right, everyone who reads after that write will actually get the latest value, right? That's how you can kind of define like consistency for a single node at a single thread level, right? So but the problem is, okay, fine, so why don't we then, I mean, if it's so simple, right? Like so because we keep seeing so many issues with consistency, so then why don't we simply stick with it? Obviously we can't, because the ultimate model that we actually want, right? Like, so where we want fault tolerance, right? Which means your data cannot be just in one single node. We need replication for fault tolerance, right? You cannot avoid it, not just for fault tolerance, right? You need replication for higher read throughput and a lot of other cases where replication kind of makes its own case, right? So given the fact that we have a way of doing it, but unfortunately we can't stick with it, because when we are building these highly scalable distributed systems, we need replication, we need fault tolerance, and once the moment we introduce replication, right, so then we actually start getting into all the issues with respect to the replication lag. So I just pasted some content that's actually from that we actually saw in the replication chapter, but probably good to kind of go over it, right? Like, so the moment you have more than one copy of your data, right, like, so in more than one node, right, like, so then I think I usually look at as three different problems that you can actually have, right? Like, so one is like read your own writes, right? Like, so like you might actually I would be the client who would have written it, but when I try to read it back, if I'm not going to a replica that contains my write, but if I'm going to a replica that to which my write has still not yet been replicated, then I might actually look at I'm not be even able to see the value that I wrote, right? So that's your read your write inconsistency, right? And similarly, something similar with monotonic reads also, right? Like, so not necessarily my read, like I actually try to go and look at a particular value. I see the value not specifically written by me, but let's say I do a refresh on the page, right? Now, let's say the request actually goes to a different node, a different replica in the system, which doesn't have the latest value, right? So now I'm kind of going back in time, right? Like, because I actually just saw value, the counter value being 100, right? Like, and then suddenly I again refresh and I see the counter value being something like 95 or something, right? Like, so I'm kind of going back. So that's called monotonic reads. And then we also have this causal inconsistency, right? Like, so this is again like when you have your data that is actually partitioned across multiple nodes, like some of these partitions could be they could have very little replication lag. Some of these partitions could have very high replication lag, in which case you have this psychic answering, right? Like, like when you display a kind of when you see this set of a chat message, you actually see the answer coming before the question, right? Like, so mainly because of the fact that like the partition where the whoever actually gave the answer, it's like it had a very little replication lag, in which case like it got replicated fast. And when I actually tried to pull data from there, I was able to pull that answer, right? When I was trying to pull the data from the partition where the actual question should actually go, I was actually trying to pull it from a replica that was actually lagging a lot behind, right? So when I pull the data from there, I don't actually see the question, right? Like, but when I now display the global view, I actually display the answer because I read it, but I don't display the question because like the partition that I read where the question is supposed to be is still not yet fully replicated, right? Like, so you guys kind of see, right? Like, so the reason we even go a little bit in depth into these things is because this is exactly the reason why getting consistent data in distributed systems is hard, right? Like, so we have to replicate, and the moment we keep data in more than one, I mean, can we make the replication completely synchronous? Yes, we can. And then only reply yes to the client. But like having, especially with the kind of unreliability that we have established these networks are and these nodes can provide, right? Like, if we wait for all the replicas, okay, let's say we have a model where we wait for all the replicas to get the latest data, right? Like, before we even say yes, right? You guys can imagine, even if a single node goes down, right, which is supposed to be a replica for this particular data, I can't actually complete my write, right? Like, the system becomes very highly unavailable. Even in the case of, it becomes completely not fault tolerant, right? Like, even there's a single node going down, in spite of the fact that I might actually have five nodes to the data, right? Like, if I have to be fully synchronous, then I have to be really highly unavailable, even in the wake of a very small network outage, right? Like, so, or even a node problem, right? So all this is again adding to the fact that what are the issues with the replication, right? And then, so I think this is probably the most beautiful definition of eventual consistency I've seen, which Kleppman gives, right? So like we all know that eventually consistent means that, like, okay, fine, at some point of time they'll all get the latest data, right? Like, so let's say you have 3 replicas, at some point of time 3 replicas, right? But the way he puts it is so beautiful. What he says is like, like, let's say you stop writing to the database, right? And then you wait, like no more writes, right? Like all the writes have stopped, and then you wait for an unspecified length of time, right? Like, because you don't know when all your replicas will be in sync, but you wait for an unspecified length of time, eventually all read requests will return the same value. Right? That's one nice way of putting what eventual consistency is, right? Like, so you stop the writes, and then there will be a point up to which, like some of your reads might return the old value, some of my reads may return a new value, right? But after a certain point, all reads will start returning the new value, irrespective of which replica it touches, right? So that point, they have all become eventually consistent, right? And one way to kind of look at it, the diagram that I have here is, like, it's like, like up to some point, they are not consistent, right? It's like false, false, false. And after a certain point, every single read will start returning true, right? Like, so that's the eventual consistency model that we saw. And then we also know that, like, it's a very weak guarantee, right? Because you have to wait for an unspecified length of time, and in the time that you wait, right, until that convergence time, what they call it as, right, your reads could actually like it could return old values, it could not return anything, because like it's an insert and it's not there in a replica. So like this whole replication lag basically gives a huge blow to this eventual consistency model, right? So which means that, like, we can choose to provide stronger consistency models, right, than eventual, but we'll always have to understand the trade-offs, right? Like the moment we say, what, I'm going to give something much more stronger, right? Like, so there is going to be a hit on the performance, right? And as I kind of mentioned, like, I can make the entire replica system, I can make it synchronous, right? But it is going to be less fault tolerant. Like, even if a single node fails, I cannot like succeed my writes, right? Like, either I have to fail the write because, hey, what, I can't write to all the replicas, which means, it's a synchronous model. Sorry, the write failed, right? Like, so I have to be like, the under any kind of small issue in the network or the node, the system will become unavailable, right? So but still, is there a way, or is there a very strong consistency guarantee? So that's what actually we are going to see today, which is actually called as linearizability, right? So, and it's supposed to be the strongest consistency model in use in practice. And I think Spanner kind of provides linearizability. They have a different word for it. I think they call it as external consistency, right? Like, so, but linearizability goes by different names based on kind of who implements it in their systems. Spanner referred to as external consistency. And the idea of linearizability is very simple, right? Like in the beginning of this session, we actually saw that, like, what if there is only one replica, right? Like, and to which the writes are atomic, right? Like, then we don't have any issues. If, okay, irrespective of what my distributed system is, irrespective of how many replicas it has, can it provide the abstraction of a single replica system, right? Like, with completely like not exposing the user to any kind of replication lag, right? If you can do that, right, so which means that you have made a system linearizable. You guys get this, right? Like, so it's like, you have a distributed system. When can I say that the distributed system is linearizable? I can only mention it as linearizable when the distributed system behaves as though there's only one single copy of the data. All issues with respect to the replication and the replication lag are completely hidden and handled inside by the system. If I can give that interface and guarantee to my external users, right? So that's exactly when I can actually call my system as a linearizable system, right? Like, so when I say that, like, it's a strong consistency guarantee, it simply means that, like, I give the user the abstraction of a single node, single replica system, right? So, and as I say, right, even though there may be multiple replicas in reality, right, like inside my system, but I can give them this abstraction saying, you'll never be able to see an older value, right? Like, as if there was only one single copy to which that write went, right? So, and that is why they actually, every time so the one way to, to quickly associate something with linearizability so that the concept comes to my mind is like this recency guarantee, right? Like, so linearizability always says that, like if there is a recent value to this particular data, all the reads after that will be able to see that recent value, right? So it's kind of a recency guarantee that they are ensuring, when they say that the system is actually linearizable. Right. So okay, so this one, right? So let's actually look at what's happening in this particular diagram, right? Like, so this. Okay, right. So there is actually I think this is a game scoring system, right, where there is an actual insert into the final scores where the game is actually ended, and insert reaches the leader at this particular point, right? So it reaches the leader, and then there are a couple of followers to which the leader replicates this specific final score insert, right? Like, so this is my follower one. So and the follower one, it actually reaches faster, right? Like, so at this particular point, it actually gets executed on follower one, but my follower two is actually lagging behind, right? So it only reaches, that insert statement only reaches and gets executed followed at a later point of time. Now we actually have two different observers, right? Like, so Alice and Bob, who are trying to look at the scores, right? So what's happening is Alice at this particular point, right? So Alice, she actually looks at the final score, and then she sees that the final score is there, right? Like, so, and then like she knows that, like Germany has won the World Cup, right? And then she kind of like, like let's say she calls Bob, and then she kind of communicates through a back channel to Bob saying that, hey, you know what? Um, Germany has won the World Cup. I can see the final score, right? And when Bob tries to refresh it, right? So Bob is not able to see that final score yet, right? He's not able to see the fact that Germany has won because he is actually reading from this particular replica to which the data is still yet to arrive over here. All right. So you guys actually see how this particular system violates linearizability, right? Because you actually have a read. So this is your first read that happened over here, right? This is your R1, right? So this R1 is actually returning a latest value. And then you actually, the R2 actually starts, it's not a concurrent read, right? The R2 starts after R1 completes, because I think that is why they have this back channel thing that they're talking about, right? Alice has seen it, and then she basically goes and tells Bob or calls Bob and says, hey, you know what, Germany has won, right? Like, so we know for sure it's not a concurrent read, right? Like the R1's effect has been seen by someone, and then it's being propagated to some to Bob, and then Bob refreshes it. So R2 for sure happens after, right? But here you're actually seeing a stale value over here. You guys see that, right? Like, so, like this is actually an asynchronous replication model, right? Like, so, where the replicas are, the followers are basically updated in an asynchronous manner. One gets the data fast, the other gets the data slow. And and then when there are two observers who are looking at these two replicas, they actually see a different a system, right? So there is one small thing that we might want to notice over here, right? I think the book also insists on that, right? What if Alice has not called Bob and then told Bob that the final scores are there? Do you guys think in that scenario, if that read from Alice was missing over here, do you guys think this system at that point of time behaved in a linearizable way?
Yeah, it would, because Bob doesn't know, and when the once the replication is done and Bob queries the system, he will see that Germany won the World Cup. So Bob would never know that there was the replication lag, like in the system.
Exactly right. So basically there was never a system, right? Like, so the way we defined linearizability has to do, okay, sorry. Okay. So the way we define linearizability has to be something like this, right? Like, once you start getting your latest reads observable, right? Like, so after that, it always has to be that latest one, right? Like, so if Alice hadn't made that read, right? Like, so which means that even though it is there in replica 1 and it's not there in replica 2, but that read is not yet observable outside, right? So even though when Bob sees an older value, it's still fine, right? Like, so because no one has actually seen the new value yet, so it's still fine, right? Like, so, and then eventually he'll actually start seeing the newer value, right? So that's the kind of that's the kind of definition that we are giving to linearizability, right? Like, so the effects become visible at some point in time, right? And once it becomes visible, it has to be maintained, right? Like, it always has to be the latest value from then on.
So this is something I did not understand, because we were saying that the definition of linearizable is that it should behave like there is only a single node, right? But in so uh, but if the writer who has written the request, if he has got a successful response, and if someone else is reading the data, if he is seeing the stale data, although the writer and someone else who is reading, they have not talked to each other, but if he's seeing the stale data, isn't it behaving like isn't it not behaving like a single node system?
Like, yeah, so if, like, in this case, right, like, so if that read from Alice wasn't existing, right, like, so then it the behavior is still kind of linearizable, because, like, no one has actually known about that, no one knows about that older value, that the newer value, right?
Mm-hmm.
Right. Let's so in so for all we know, let's say that Alice's read was completely non-existent, right? Like, so then it is kind of, so even though the write already happened over here, and then there is this async, there is one, like, as long as nobody has read from that that follower one, right? Like, and then the very first read actually had gone to follower two, where he is actually not able to see the results, right? Which is still fine, because linearizability is more about, like, once it gets exposed outside the system, right? Like, so from then on, it has to be maintained, right? But as long as it's not exposed to the system, it's still okay.
Okay.
Right?
Yeah.
But
Okay. I just think then it's still a bit different from a single node system, because in a single node system, like, still the second, even though someone else has not seen it, but still you will see the updated value, right? But here we are saying that you might not see the latest up-to-date value.
right, yes, you might not see the latest update value, because that write is still kind of in progress.
Mm-hmm.
Right, like,
Yeah.
so because we have multiple replicas over here, right? The write is still in progress, so it's like, even though it is completed in follower one, but because no one has actually read from follower one, right? Like, so, and it's not yet completed by follower two, and the read is actually kind of going into follower two, right? Like, so, which means that he's not able to see that latest value, right? So which can still be considered okay.
Mm-hmm.
Right, like, so I can see your conflict, right? Like, and I can actually kind of relate to it. It's just that the if that Alice's read hasn't happened, then, like, according to this whole system, right, like, so that particular write has not even been completed, right? Like, so because that write has not yet been exposed outside.
Yeah.
If Alice's read, the Alice's read is the only thing that exposes the fact that there is a newer value, right? Like, so if we can, if that particular exposition over there didn't happen, right? Like, so then, and let's say for some reason, Bob is the very first one who reads without Alice reading it, and even though he sees an older value, right? Like, so it kind of doesn't violate the property of linearizability, in the sense that, like, that recent value has not yet been exposed outside.
Mm-hmm.
No, I think, like, this is just this example. This just tells that what is the problem. Like, this is an example of non-linearizable system. I think in linearizable system, it says like there can be of multiple followers, but like when the any Alice or Bob it makes a query, they will see the same result. So that can only happen if the replication is synchronous. So here I think they're just depicting the problem, uh, like because I think in the recent examples they explain like how we can fix the problem. Yeah.
Okay, sure. I think that's another way. Yeah. So I mean, like at least like this particular diagram basically just talks about how the linearizability gets violated.
Okay, I have a let's say suppose there's only one node. Okay.
Right.
Then let's see Alice is read from the leader, but it read from the leader at the time that leader have not completed receive the write request, but they have not complete the write request yet. What would that value return to Alice?
It could it could be anything, right? So I think the diagrams over here is exactly kind of going to talk about that particular case, right? So because the server basically like it gets the write request, and then it actually completes it at some point of time, and we don't know exactly at what point of time it takes effect within the server, right? Like so it would take effect at a particular instant in time that write actually completes in the leader, right? So before that Alice would be able to see the value that is older, and let's say there is one particular point called as a linearization point, right? Like so after which that particular value takes effect. After that then the Alice should be able to see the later values.
Okay.
So you're always having this particular thing, right? Like so the diagram I think probably is going to explain better, but let's say you have this, like your server actually got the request over here, right? So the request actually gets into the server at this particular point of time, and let's say the server completes the request at this particular point of time, right? But for the client, right, so for any client, right, so they are not actually aware of this whole when the server, they just know that like at some point of time the request was actually sent to the server, right? So probably the request was sent to the server over here, right? And then they probably received the response somewhere over here, right? Like so they sent the request, the client sent the write request over here, and then it actually received the response over here, right? So let's say this is the point where the server received the request, and this is the point where the server sent the response, right? So at one of these particular points, right, somewhere in between, the server received the request and server actually executed that particular request. Until this point, whatever clients actually read from, right, like so they will actually be able to see the old value, right? And after this particular point where that the switch actually gets flipped, right, like so where like the old value turns into the new value, right, like assuming it's an atomic, right, like so then after this point, any of the clients who are actually kind of reading it, they should be able to read the value which is actually the later value. You guys see that, right? So even though the original client that actually sent, so that actually we'll see that in the example later, right? So in this case, the original client is actually getting the okay. So this is the okay write response. So this is the okay write response that is actually the original client that actually sent the write. Right? This is a write request. It's getting this okay write response somewhere in the end, right? But even before this, let's say there was a client 2, right? Let's say there's a client 2, and this client 2 actually sent it probably maybe it's located on the same rack as the server, right? So which means it has a very shorter latency to the server. So it actually sends a read request over here, and then the server is able to respond, and then it actually gets this the read value over here. So this particular client 2 will actually see the later value. Even though the original write, the response, the acknowledgement for the original write itself is going to reach client 1 at a later point of time, the client 2 will actually see the later value because of this inflection point where the value changes in the server.
Yeah, very good.
You guys see that, right? Yeah, I think more of your questions are going to get clear in the next in the next one, right? So because this is what they are talking about, right? Like, so you have these you look at three different clients, and you look at a behavior where it's in non-linearizable, where, you know, like the starting point of these blocks, right? So all the starting point, it actually this is the point where the request was sent, right? And then this is the point where the response was received, right? This is all from the client's view, right? So why is this particular system non-linearizable, like the way these clients are actually observing these values? Can you guys kind of see why this could be, or maybe it's linearizable, right? Like, so can you guys argue for the reason why this is linearizable or non-linearizable, right? Like, based on the fact that, you know, like in a linearizable system, you know, we understand that, you know, like there's always this condition where, you know, up to a point where we see the old value, and after that we actually see the later value, something like this. So the write that is going to change the value is coming over here, and the server is going to send an OK over here.
Yeah.
So one thing you need to take into account is how the reads are structured, right? So reads, whether they're dirty reads or, you know, persisted reads, or it is just like a read committed reads, right? So most of the time we want, it depends on the applications. If it's a banking application, you always want committed reads, right? Or if it's just like some kind of blog or something where you don't care about whether the data is updates, then you can actually have more stricter reads. So based on the application, we can actually set the reads. But in this scenario, if we say that it is we need consistent data like bank or something, then we can say that only after the write is fully committed, only then give me the data. So in the first scenario, right, you see that there's two scenarios. One is Alice and what's his name, Bob, right? From what Alice is, if Alice is in one zone, right, and in that zone you only have server one where it gets the data, and Bob is in a different zone where you only have access to server two where you get the data, and there's a replication lag of probably 5 seconds or something. So whoever gets the data first will actually have different answer than other. So in the context of consistency, yes, data from what Bob and Alice saw was correct. But is it correct? It's not. But so in that case, where caching and other things probably we'll see later, how to, you know, get consistent once a read is exposed, that this is the Germany won. So the same message should be there. So backend should be, you know, morphed into like abstracted to from which replica it's coming.
Right, I agree. So I think, yeah, so in at least like in the context of the examples that we are seeing right now, we are assuming that there are no transactions.
Yeah.
Right, like, so
Mm-hmm.
we are yeah, but yes, it's like using, so one of those transaction isolation levels would be able to, there's a small correlation between those transaction isolation levels and the kind of linearizability that we can actually support, right? Like, so there is an intersection between those two things, right? Like, so, but I think currently all the examples that he discusses are, you know, like, assume that all these are like individual operations that are not done using transactions, kind of.
Yeah, so in the first example, it shows that, I mean, each client can read either 0 or 1, so we are not sure what value they will read. So that's why actually it could be possible that the client A read the value 1 and B read value 0. So that's why it's not non-linearizable. But in the second figure, it shows that as soon as the client A start reading 1, so if we make sure that client B will also see the same value.
Perfect. Right. I think that's the explanation for these two diagrams over here, right? Like, so the first one, we kind of see that in the first one, we kind of see that, you know, those three reads that we see in the middle, right? Like, so they can actually either return 0 or 1, in which case it could have happened that this read returned 1. Sorry, this read returned 1, this read returned 0, right? So which means that it's kind of going back in value. It's not getting the latest one, right? But we know for sure that this read happened later, than the first read, right? So that's why this particular behavior is categorized as non-linearizable, right? But in the second one, if you guys look at that, so there we can actually see that if it's guaranteed the way in which they are showing, right? Like, so where, like this at this point the read was 0, this point the read was 0, but from here the actual write started getting reflected, right? Because as I said, there is this particular point where the switch got flipped because of the write, right? So, and as long as after that flip switch we can guarantee that all the reads are seeing the latest value, so then that particular behavior becomes linearizable.
Yeah, the key thing is once the read starts before the write, then it giving whatever was the previous value.
Yeah.
But after the write starts, maybe this is dirty reads, right? Because
Yes.
the write
Yes.
is not yet committed,
Yes.
and you're reading read with no lock or something, right?
Yeah,
So
this
in
is
that
like no
scenarios,
transaction or something.
yeah, no transaction. So in that case, the client A and client B, even though read started, it may roll back, right? Client A sees 1, but maybe if the transaction is rolled back, then again it may be a different value. So, but in this case, it shows 1 here and 1 for the client B because they're reading dirty reads. But once it's committed, then client A actually sees um, actual committed read.
Right. Yeah, exactly. Yeah. So
Yeah.
in this case, it's like dirty reads are actually permissible. So
No,
because we are assuming a system without transactions.
that is fine, but here these are considered, these are three different replica. So that dirty read, the transaction will be, I mean, we can control on one system.
Right?
Yeah, internally, why they are seeing those 3 different values, it could be the reason. Yes.
Yeah, and then as mentioned, I say linearizable is not the same as transaction, right? So
Yeah.
why would we say dirty read or dirty write or committed in here?
Yeah.
I mean, if this was like a single node system and we are seeing this particular behavior, I think that was the reason why earlier Praveen was mentioning about the dirty reads, right? But the second Praveen who actually mentioned about the fact that these are coming from different replicas, so then we don't actually have to worry about dirty reads over in that particular scenario. Because you're kind of getting it from different replicas, the clients are observing the values from different replicas, right? So in that case, yes, you don't have to worry about whether dirty reads are permitted or not.
So, Johnny, I have a question. So, how this linearizable feature is supported by a distributed system? Like my understanding says, like it can only be done if the replication is done synchronously. Without that, it is not possible. But do you know, like any system, any like DB which supports this linearizable and how it is actually implemented?
Yeah, I think you're on the point when you mentioned that like it's hard to achieve linearizability, right? Most distributed systems do not guarantee any kind of linearizability, except for those systems that actually are implemented as consensus systems, right? Like so, Zookeeper, for example, or any system that implements Raft, right? Like so they are able to achieve linearizability, not just using this completely synchronous replication mechanism, but they actually have a way of doing it via a protocol called total order broadcast, which we are actually going to see later. But any consensus system in a distributed system, they actually have to be linearizable, because a lot of crucial decisions are actually based on what the consistent system says, right? So like Zookeeper, for example, is they implement linearizability using total auto broadcast, and Raft and Paxos, they are algorithms that guarantee linearizability.
So can we say that, I mean, like Cassandra, writes use the quorum, so that is one way to achieve that?
We'll actually see later in the same chapter, we'll actually see why quorum, even though quorum reads and writes kind of look like they are linearizable, right? Like, so because we are trying to get that, we actually Martin Klebman has a very nice example that kind of breaks that that myth, that like that we can achieve quorum linearizability using quorum consistency. Even if we have a strict quorum consistency, right? Like there is nice example we'll see later where linearizability actually gets violated in spite of guaranteeing quorum consistency. But it's actually, but what he's saying is pretty close in the sense that from the outskirts, it kind of looks that like, hey, I want to get the latest value, right? Like, so as long as I'm reading it from the majority of the nodes, and if the majority of the nodes has seen the right, like, which is what your quorum guarantees, right? More than n by 2 have actually seen the rights, and if I'm going to read from more than n by 2, then probably I am going to always see the latest read. Right, like so there are scenarios where we'll see mainly in concurrent scenarios we'll actually see that, right? Like, so where you will not be able to achieve this linearizability using quorum consistency.
So one point I want to mention here is, so if we make this definition like this, that after anyone has read the new value and the client who has written the new value, he has got an okay response, then everyone should see the latest value. Is that a more stricter definition of linearizability than just saying that after one of the client has read the latest value? So like my point is, what about, so the client who has written the value, he has got the okay response.
Mm-hmm.
And but when others are reading, they are not still seeing the latest up-to-date value. Will that system be linearizable? Because although like I was the first one who came to the system to read the value, and like but what if I'm seeing the stale value? Is that the system linearizable? And although the client who has written the value, he has got the okay response that his write was successful and my read came after him.
Okay, so that's an interesting scenario, right? So what if the read, but no one has read that particular value so far, right?
Yeah,
But
no one has read.
I think it should be. I mean, if
It
the
is linearizable still.
if the database supports that read your own rights, then in that way, yes, it should be. I mean, others should get the same value.
So we should get the same value, right? And that's what I don't see why they have not mentioned that in this book. Here, the definition is that if anyone has read the latest value, then only you should be seeing the latest value. But my point is not just that. Even if the person who has written, who is making the write, if he sees okay response, then after that, like everyone should see the latest value, then I would say that the system is linearizable, not just by this definition, that if anyone has seen the latest value, then only after that it should show the latest value.
No, but
Like,
Abhishek, think about if your system is not read your own write support, right? So even though you write that value and you get the okay, and if you try to read by yourself, it could be possible that you will not get the
yeah, so
latest value.
in that case, the system is not linearizable, right? I'm saying if the system is linearizable, then the definition should not be just that if anyone has read the latest value, after that only I will see the latest value. The definition should be either this, or if the client who has written the value, he has got the okay response, then also after that I should see the latest value. Then I will say the system is linearizable. Otherwise, I will not say the system is
No,
linearizable.
no, my point is that you get the okay, and when you're trying to read, you are still getting the old value, right?
Mm-hmm.
So
Mm-hmm.
they're also getting the old value, so which means that everybody is getting the same value. Now you have the different problem. Like you updated some value, but you are still getting the old value.
But how is that possible? Because I just wrote in my replica, so I should get the latest value, right?
No, but if you have 3 replica and your read request, when you are pulling the value, it's going to the different system. So author mentioned that in the replica chapter, read your own write, solve that problem. When you try to update your data up through the single leader. And Johnny also covered that during the start of the session, that those three issues with the the leader-based replica, read your own writes, monotonic read, and there was a third one where the order of these messages was different.
Right. So I think in addition, right, there is one more thing, right? So we are looking at individual instances of reads and then saying, okay, this behavior is linearizable or this behavior is non-linearizable, right? But let's say in a system that is implemented and says it's always linearizable, right? So in which case, if the client has actually if the client has written it, right, and if it actually gets successful, right? So if the system is always supposed to be linearizable, if you guarantee it, right, then you will never be able to see an older value for any reads either by the same client or other clients after that particular thing. Right. So like what I think Abhishek proposed, right? So that's one instance of a particular thing where he says that, like for example, something like this, right? Let's see. Sorry. Let's say we have something like this, right? So this is my client, and then let's say this is my replica 1, this is my replica 2, and then this is my replica 3, right? So what's happening here is, let's say this is probably my leader replica, for example, right? So the client actually writes it, right? Let's say the value gets turned from 0 to 5 over here, right? But these guys, they still haven't actually got the replicas haven't got it, right? So but the client actually gives an okay over here. It gets an okay over here, right? If a read happened, if let's say the read 1 happened, we are only looking at one single execution of reads, right? Like say the system is such that there is a read that happens over here, right? Let's say client 2 reads it and it actually reads here. It's fine because it's actually going to get the old value 0. And let's say client 3 also reads it, maybe either from here or from here. It's fine as long as it gets the old value 0, right? But at some point of time, someone starts reading from like from your actual leader replica, right? Like, so which means that the value changes from 0 to 5 and it's exposed to the outside world, right? So a linearizable system should always be able to support that, right? Like, so if someone has actually implemented a linearizable system, right, like there is no way in which you can actually see this particular I mean, they cannot have a system like this and call, even though this one single execution, right, like you can call that single instance as a, oh, this looks like a linearizable reads, right? That's what these examples are kind of telling us, right? We are looking at one small instance saying, okay, if it was like this, then we say, okay, it's linearizable, right? Which is fine, right, for that particular instance. But if the replication is asynchronous, like mentioned over here, right, and you will always be able to find examples of other examples where if you have a system like this with 3 replicas and only one gets synchronously updated, you will not be able to make it linearizable, right? Like you'll always be able to find another instance where like there is this client C5 which actually reads from here and it actually gets the value, and there is a C4 that reads from here that gets 0, so it becomes non-linear, right? So like in a non-linearizable system, I think the key thing is, in a non-linearizable system, like some instances you can always see as like linearizable, right? Like because of the way in which they happen. But there'll always be instances where you can actually see that they are non-linearized, right? But if a system has guaranteed you that it is linearized for sure, then all instances that you actually observe, right, like all instances that you observe will be the fact that they'll always get the latest value. Does that help your question, Abhishek?
Yeah, right. So so I mean, basically we are saying this, right, that if the system is linearizable, then then after getting the okay response, whoever is reading, he should be reading the latest value.
He has to, exactly, yes. He has to get the latest value. There is no way for a linearizable system to give him an older value, because then we'll be able to, if it gives older values even after the client gets okay, right? Like, so then that system is not linearizable.
No, yeah, okay, yeah, great.
Okay, so
Abhishek, I mean, still, I mean, my concern is that you are saying that, I mean, after getting okay. So if you see the figure, that picture, could you go up a little bit? So the second picture. So here that the C did not get the okay yet, but system is, and read happened, system is linearizable, right?
I think maybe the DB, the write x equal to 1 that is written in the DB, only client didn't get the okay response. So I think that is mentioned in later in the chapter as well.
Yeah, so that okay is that, I mean, it could be possible that the client may get the response, the response is a little bit delayed due to
Delayed, right?
some other
Exactly.
network issue.
Exactly. Yeah, I think I think this actually even more answers Abhishek's question better, right?
Yeah.
The reason why it's not dependent on OK is because like the whoever wrote it, right, at some point, at some inflection point or linearization point, it already happened over there. But from the client's point of view, right, like he might actually have a huge network delay before he actually sees the OK, right? So how can even the server guarantee that like only after that this client sees OK, I'll actually reflect this value outside, right? Like from the server's point of view, that switch got flipped when it flipped it.
Exactly.
Yeah, no, that's a good point. But like the thing I'm saying is that once you have seen okay, then definitely everyone should see the latest value. So my point was, let's say client A, which is reading, which gets the value 1, let's say if it was also getting 0, client B was also getting 0, and client A, which is making the read after client C has got the okay response, if he was also seeing 0, then although nobody has read the latest value up till now, right?
Mm-hmm.
But still I would say the system is not linearizable because client C knows that the value has been written, but still someone else is seeing the stale value.
Right. I agree. So that two things, right? Like so, even though they look the same, two things that definitely that system is not linearizable for sure, right? But if you just consider that single instance of reads, then we are simply saying, I think that's what this all these pictures talk about. Right? That single instance of reads, it looks like it's a linearizable read, right? Like because like you're seeing 0, 0, 0 and then 1, 1, 1 after that, right? So, but that system that where you're saying that like even after the write succeeded and someone is seeing the older value, definitely if the system exposes things like that, you will always be able to find examples in that system which is not linearizable, which means that the system itself is not linearizable. Yes. Amazing. Okay, so I think we actually so we kind of I think the one good thing I always find in this group is we always discuss topics beforehand, even before we come to them, because people are really brilliant at figuring out things, right? So and I think I find it in every single meeting. So because what we kind of discuss is what is being kind of mentioned over here, right? Like so like there is this inflection point that we are talking about, right? Like so even though whatever that we see, this full boxes is the starting of the box is when the request was sent and the ending is when the response achieved, right? But when it actually got executed, there is always this set of the linearization points, you can call them, right? So this linearization point, right? And basically, to characterize a system as linearizable, what Martin Klapman basically says is, he says, like if you look at this inflection points in time, right, like so, then you should actually be able to see the values move forward and they should never move backward. And I think this even more answers Abhishek's question, because if you actually look at the inflection point, right, like say this particular write actually happened at some point. So let's say that write's inflection point is over here, right? And then let's say there is a read that happened, right? Let's say, and then that read happened at this particular instance. If this was 2, right? And then if this was actually still 0, right? So it's actually not, because we are trying to like we are kind of trying to connect these different points at which those instances were executed, and we are able to make sure that the system always moves forward in time, which means that there is never a point where we are able to see one of the older values, right? And this example, the reason why they're saying that, like the final read, right? They're saying that last read is not linearizable, right? Like they're only considering one instance, right? They're not talking about the system as a whole, but they're saying that that last read, at least whatever the system is, the way the system behaves, the last read is not, because like you see the CAS operation happening over here, right? So this CAS operation happens over here, and the effect is already, so this is, let's say this is #1. The effect is already observed here at #2, right? So which means that at #3 we should be able to see the effect if it was a linearizable sequence of reads and writes, right? But in this case, because we are not able to see that, right? Like for some reason, whatever the system is actually able to expose an older value, even though it exposed at some other points of time previous values, right? Like, so because of that, this particular example that they have given is non-linearizable.
Johnny, could you repeat the last part, like #1, #2, and #3?
Yeah. So sure. So what's happening here is, like at #1, right? So there is a CAS operation, right? So where it's actually saying set the value to 4 if the older value is 2, right? So and if you guys actually, so let's see, right? So if you look at it, so this is the point where that request actually came to this particular, I mean, the request was sent by this particular client, right? So this is the point at which, and this is the point, right? So this middle point over here, right? So that is where it actually took effect, because of which, because it has taken effect at this particular point, right? So #2 is, there's another client who's trying to read, and he is actually able to see that, right? Because it actually happens after that particular point where that switch was flipped from 2 to 4, right? But what is happening at #3 is there is a different client, and for whatever reason, because the system is not linear, the actual server where all these reads and writes happened, right? Like, so where the values are stored, because it's not linearizable, like you actually have another client which happened after #2, right? But it's actually seeing this older value too, right? So you're kind of, so if you look at the way these values were, so 2 came into existence, 4 came into existence at this particular point, and then this guy was even able to see the 4, but then at a later point of time we actually changed, I mean, another client was able to see 2, so because of which we characterize this particular behavior of the system as non-linear.
Yeah.
Does that answer your question?
Yeah.
Right? So it's I think he's just giving more and more examples. Previously he was just using reads and writes, and now he's introducing and an atomic compare and set operation, a CAS operation, and then he's kind of expanding this example, saying, like at all these points, if you can connect these exact linearization point, it moves forward. But there is this last place where you can actually see the system behaving. I mean, he's not talking about the actual system and why it is happening and stuff, but he's just, from the client's point of view, the client actually sees something backward. So which means whatever the system is, it's not linear.
And so in this case, if like the number 2 did not happen, just number 3 happened, the system is then the system is linearizable or not?
So if the number two did not happen, and then the number 3 happened, right? So then this is, I think if you that particular sequence look, as I said, right, that particular sequence looks linearizable, right? Like, because we are just defining it based on the reads. But if that was the case, right, the system as a whole will exhibit so many other behaviors that will be non-linearizable. So the system will still be non-linearizable, but we, like as you said, right, like, so like in any non-linearizable system, you can always get a sequence that looks linearizable, right?
Mm-hmm.
Right?
Okay.
Like, so depending upon which replica, for example, it's a completely non-linearizable system, but it so happens that client A, B, and C always read from the master, right? Then you look at that sequence, it looks linearizable, right? So it is still linearizable, but you're getting it from a non-linearizable system, right? But you only characterize the system as linearizable if all the reads are linearizable, right?
Yeah, that's a very good explanation. Yeah, I agree. Yeah.
Okay, so yeah, and the other thing that if you guys would have noticed, right? So one of the things, it's mostly because of all this, like concurrent requests that are happening, right? Like, so like there is so usually you will have a write, and then there are multiple reads that are happening during that concurrent write, during that write, which are all like concurrent transactions, not sorry, concurrent operations happening when this write is in progress, right? So that is one very typical characteristic of a non-linearizable system, right? Like, so if you guys actually see that, right? What else is he talking about here, right? So yeah, as I said, this model doesn't assume any transaction isolation, right? Like, so we are kind of talking in a system where we are looking at simple individual operations, right? Like, so by each of these clients, single reads or single writes and single cache operations. Okay, so coming back to because linearizability and serializability are usually there is an overlap actually, right? Because you can, depending upon how your serializability is implemented, you can actually see whether you can implement linearizability or not. I think that's the bigger picture over here, right? Purely talking in terms of what they are, your serializability is a totally different concept, right? Like, so because it's one of the transaction isolation levels, right? Like, so when you have these multiple transactions where each transaction can actually touch upon multiple different objects, right? Like, so like serializability talks about like, are the results produced as though these concurrent transactions executed in some kind of serial fashion, right? Like, so that is all your serializability is with respect to the transaction isolation levels, right? But linearizability is like with respect to those individual operations, right? Like, so I think in this particular case where we are actually talking about like the read and write of those register values, right? Like, so that we are trying to modify, right? So with respect to those, like, are you able to observe that recency guarantee, right? Like, so like where at some particular point like if the system actually changes the value because of the write, all the other points after that, are they able to, all the reads that actually happen after that, right? Are they able to observe that latest value you see? So so yeah, in essence, a linearizable system should always guarantee to return you the latest value. And whether
one quick question, could you explain, let's say for the serializable, let's say it's okay for that serial order to be different from the order in which transaction was actually run. What does it mean?
Yeah, so what it actually means is, like, if you, let's say from the client's point of view, if client, there are 3 different concurrent transactions that are happening by, let's say, 3 different clients, right? Let's say you have, let's look at this. You have C1 and then you have C2, right? Let's just look at C1 and C2, right? And then let's say from the client's point of view, right? Like, so if you observe this C1 transaction going somewhere like this, and then C2's transaction going somewhere like this, right? So the serializability does not guarantee anything based on how these clients are observing these transactions, in the sense that as long as your actual server, right, either executes it as like what, let's say this transaction is T1 and this is T2, right? It either executes, it gives you the result as though T1 first executed and then T2 executed next, or T2 first executed and then T1 executed next, right? So this is still serializable. That's what they're trying. Yeah.
Okay.
That's what they're trying to kind of mean, like, because the reason why this this specific literature or the way they're wording it comes because like these 2 transactions are concurrent, right? So when these 2 transactions are concurrent, right? Like, so like these clients can see them in different orders, right? Like, but serializability only guarantees you the fact that, you know, they will produce, the effects will be produced as though they were run serially, even though like you are not guaranteed. Like, for example, from C1's point of view, hey, you know what, like T1, I started T1 first, and then I see that T2 actually started later. So it means I should see T1 and T2, right? So that effect is not guaranteed by serializability, right? But what it can guarantee you is when your transaction was run, when T1 was run, it will guarantee the fact that it ran as though there was no other interference from any other transactions. It was the only transaction that actually ran when that got executed.
Okay. So for linearizability, then C1 must happen first before C2, right?
Yeah, in effect, if you can guarantee that, right? Like, so if we think about it a little bit, if we can even guarantee that there is a total ordering of the way, which is even visible to the clients, right? Then you're kind of establishing linearizability on top of serializability. Yeah. So that's where that distinction actually comes over there, right? Like, so in addition to like the serializability, if you can also guarantee from the client's point of view that there is a total ordering, right? Like, so then you are essentially achieving linearizability on top.
But in this case, the total order could be anything, right? Either T1, T2 or T2, T1, but it should remain same, right?
Exactly. It should remain same, yes.
Yeah. Mm-hmm.
And so in the context of connecting serializability and linearizability, right? Like, so one thing that they're kind of talking about is that like, can I, so okay, serializability is your highest transaction isolation level, right? So given that I'm going to implement a serializable system, right? Like, so, you know, can I make the system also linearizable, right? Like, so, and it ultimately boils down to the way in which a serializability gets implemented. If you guys remember from the transactions chapter, we actually saw that there are three different ways, right? Like, so for serial, one is the actual serial execution, right? So, I mean, the system itself actually executes in serial order, right? So in which case it's definitely linear. So, and the other one is where we actually have this two-phase locking, right? So if you can actually do two-phase locking, again, it's kind of linearizable. The one thing where it is not necessarily linearizable, definitely not linearizable, probably is the snapshot isolation, right? Mainly because of the fact that whenever you use, like, linearizability actually breaks down the moment you start using some kind of a cache, right? That's the biggest, you know, like when you're not when you're not, because the moment you're using a cache, right? Like in snapshot isolation, what you're trying to do is, like, you know, you're when your transaction starts, you're basically freezing your entire database, right? You're freezing your entire system, and then you're only looking at the values, you know, like from the frozen system, right? Which is kind of which is your own system, right? So whereas there could be values that are outside this snapshot isolation, right? Like, so transactions that happened outside of this particular transaction that could have changed some of these values, but you are not actually reflecting, it's not getting reflected in whatever that you are trying to read over here, right? So that's why they're saying that, you know, like, if you implement serializability using snapshot isolation, so then they're saying that, you know, like, the system is probably not linearizable, right? So like, even if you actually have serializable snapshot isolation, right? Like, so, like, so this is something that I think we might want to think a little bit more, right? Because if you guys remember what serializable snapshot isolation does, right? Even though it actually even though it reads and writes from the snapshot, it kind of checks to make sure that none of what the other transactions did will actually affect what I'm doing, right? Like, so it only commits at a later point. If you guys remember, there are a couple of things, right, about how to MVCC stale reads and MVCC stale writes, right? Like, so where we actually started seeing about how to actually predict, you know, like, because it's an optimistic concurrency control method, I'm moving from a snapshot, right? And then when I finally want to commit, I will actually look at a few data structures to see whether something else has interfered, so that, you know, either my reads were stale or my writes became stale, right? Like, so it maintains that your transaction manager would give you that information to make that decision whether you should commit or not, right? So it still looks like that particular system might be linearizable. Don't you guys think so? Some food for thought. Maybe we can discuss this in the session, because the way I was able to two-phase locking for sure, because you're preventing everyone else from actually accessing your stuff, right? Like whatever that you're dealing with. So you can actually order those events. But for some reason, even though you're doing optimistic concurrency control and you're only committing on a SSI, like if you finally figure out that like there are no stale reads and no stale writes, right? Like that's when you are, because you still have to guarantee CLSL execution, right? So even though you're using snapshots, all right. But Kleppen still says that it's not linearizable.
Johnny.
Yeah.
The next session is up. Can we wrap up this one now?
Okay, sure. Yeah, I think that's something we can actually discuss, like why an SSI, or probably we can come up with an example as to why an SSI, because they're kind of mentioning that the reads are not linearizable anymore. So maybe it's not about actually committing those transactions, because you're reading from a snapshot, as simple and pure, right? Like, so you're reading a cache version, it's not the latest version, not linearizable. Okay, so we'll probably look at the rest of the stuff over the next couple of weeks. I think probably take a couple of weeks. And in the interest of time, thanks everyone for chiming in. It was an interesting session. Thank you.
Thank you, Johnny.
Thank you, Johnny.
Yeah.
Thanks, Johnny.
Thank you.
Thank you, Johnny.
Bye.